So if you're preparing for any competitive examination of electronics like FCAT exams or ISRO exam or any competitive examination for that matter of electronics, you can attempt the mock test and you'll be getting to know that how much knowledge or how much you're good enough in this subject. And if you like the questions, please don't forget to like, share and subscribe. And also you can find the notes of this video in the description box. Now let's see the 10 questions. So this is a mock test for digital electronics. If you're preparing for any competitive examination of electronics, you can attempt this digital electronics mock test. It will be very useful for you. Now we are going to see the solutions. The first question is, you can see the question on board. The expression for absorption law is given by dash. So from the various options given, the first option is actually giving you the absorption law. Now absorption law means it is actually absorbing of some variables. Here the first option is A plus AB equal to A. Now, A plus AB means you can take an A common. It will be 1 plus B. And this 1 plus B will be equal to 1 plus any term or any variable will be equal to 1 only. So, A into 1, that is A. Now, here you can see in this expression there is a B variable. But in the output expression or the simplified version doesn't have a B. So, it is absorbing of the B variable. So, the correct answer for the first question is option A. A plus AB equal to A is actually a statement corresponding to absorption law or the expression of absorption law. Now if you see the option D is A plus B is equal to B plus A. This is commutative law. Okay, so if the question is what is expression giving commutative law means you have to select this option. But the question here is asking associative law and hence the correct answer is A. A plus AB equal to A. Why? Because it is absorbing a variable B. It is not in the resultant expression. Okay. So correct answer for the first question is option A. Moving on to the second question. Now the question is from number systems. So I've tried to include variety of questions from various topics. The first question, so the second question is the representation of octal number 532.2 to the base 8 in decimal. That is, you have to convert this number in octal to decimal format. How to convert a number from octal to decimal is by multiplying these numbers with the powers of 8. Okay, I'll write the octal number once again. It is 532.2. So the numbers I'll write 5, 3, 2 and 2. So I'm going to write the position values 0, 1 and 2. Here it is. Since it is after the decimal, it is minus 1. Okay. Now represent these position values as powers of 8. 8 raised to 0, 8 raised to 1, 8 square. Now multiply with the corresponding number. So it will be 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to minus 1. Okay, so this will be the result and the sum of this expression will be your corresponding decimal number and that will be 346.25 to the base of 10. Since it is a decimal number, it is to the base of 10. Okay, that is 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to minus 1. Now why we are taking minus 1 is because it is after the decimal. So after the decimal it will be minus 1. The position values will be minus 1, minus 2, minus 3. Likewise it will go on. Okay. So the answer coming here is option A, which is 346.25 to the base of 10. Moving on to the third question. So digital electronics is actually one of the very important subjects. There's a lot of weightage for this subject in all competitive examinations. So try to give maximum importance to digital electronics, analog electronics, these subjects. So third question is the expression, I'll write the expression for you. Expression y equal to AB plus BC plus AC shows the dash operation. So expression is y equal to AB plus BC plus AC. And this shows dash operation. The options are A, XOR. Is this XOR operation? No, it is not XOR operation. B, SOP. SOP means sum of products. Sum of product. Is it sum of product? Yes, there are product terms and the product terms are being summed. It is a sum of product expression. Now the other options are option C, POS. POS means product of sum. So is this the products of sum? No. The products of sum will be like this. A plus B into B plus C into A plus C. So this is a POS expression. But this is not POS. This is SOP. Okay. Now the last option is NOR. No, this is also not NOR expression. Correct answer is option B. SOP is the correct answer for this question. Okay, so these terms are actually product of some terms. Sorry, these are the sum of the product terms, SOP. Sum of products. Okay, correct answer is option B. Fourth question. Fourth question is from CMOS. CMOS behaves as A or AND dash. That is, CMOS behaves as a dash. A adder, B subtractor, C inverter, D comparator. Very simple question. If you know the basic structure of CMOS. So CMOS is having a pull-up logic and a pull-down logic. We'll be realizing this pull-up using a PMOS. Pull-down is realized using NMOS. You connect these two bases and apply your input. And whatever input you apply to this CMOS input side, you will get the complement of it. That is, consider you are applying a variable A. You will be getting output complemented. So this is a basic working of a CMOS or a complementary metal oxide semiconductor logic. It's a CMOS logic. Okay. So you will be getting the inverted version. So this is nothing but a CMOS. A basic CMOS is a inverter. So the correct answer is C, inverter. Okay, so here there is VCC. I hope you can see it. So this is VCC, okay, or VDD. It is a high logic. This is the ground. Okay, this is ground. So this is a basic inverter. So a basic CMOS logic or a basic CMOS circuit is nothing but an inverter. Okay, correct answer is option C. Moving on to the fifth question. In 1 to 4 demultiplexer, how many select lines are required? So the question is from demultiplexers. The multiplexer, demultiplexer, this area is also very important. I'm going to draw the structure of a 1:4 demultiplexer or 1/4. So a 1/4 demultiplexer consists of one input. This is nothing but input bar output. Okay. And 4 outputs, demux. Now a demux and a mux, that is demultiplexer and multiplexers, have select lines. Okay, so if there is 4 select lines means it has, if it has 4 output lines means it has 2 select lines. Okay, so the concept is if there are n select lines, then output is 2 raised to n. Okay, since there is 4 we can write is 2 square, right? So the n value is 2. So number of select lines is equal to 2. Okay, so these are the 2 select lines. I hope the concept is clear. So we are discussing about a demultiplexer. Demultiplexer means it will be, that is, multiplexer combines, and in the case of demultiplexer it decombines. Okay, so there will be more output lines and less input lines. So since it is 1 to 4 or 1 to 4 demux, there is 1 input line and 4 output lines. Okay, now if there are 2 raised to n output lines, then n is the number of select lines. So here 2 raised to n is 4. Now we can write 4 as 2 square. So n is 2 here. So number of select lines is 2. Correct answer is option A, which is 2. So this is the logic which you have to apply for any demultiplexer. In order to find the number of select lines or number of output lines, you can use this logic. Okay, correct answer here is option A, which is 2 is the correct answer. Moving on to the next question, which is the 6th question. Yeah, 6th question is from flip-flops, and it is from JK flip-flop section. How is the JK flip-flop made to toggle? Now, if in order to answer this question, you should be familiar with the truth table of a JK flip-flop. We have done a very detailed video on the flip-flops. It is in the digital electronics playlist. You can watch it for your reference. Okay. So here we want to toggle JK flip-flop, and the truth table of JK is like this. There is a J, there is a K, and there is a next state Qn plus 1. Okay. And for various combinations, for 0, 0, 0, 1, 1, 0 and 1, 1, the output is like this. For 0, 0, it is the previous state itself. For 0, 1, it is 0. 1, 0, it is 1. And for 1, 1, it is Qn bar. Now, we all know that JK flip-flop is actually designed to overcome one of the problems or demerits of SR, which was, for the case of SR flip-flop, the 1, 1 state was not defined. But in the case of JK, we have overcome that problem or demerit by making this a toggled state. Okay. So in order to get a toggled condition of JK, we have to make J equal to 1, K equal to 1. Okay. Correct answer is option D. J equal to 1, K equal to 1 is the correct answer, which is option D. Moving on to the 7th question. Okay. 7th question is from shift registers. The question is a small numerical question. With a 200 kilohertz clock frequency, 8 bits can be serially entered into a shift register in dash. The question is regarding time. Okay. So the frequency F is equal to 200 kilohertz. Okay. This is the frequency. Now, we are designing a serial shift register. So, if for the case of a serial shift register, if the bits are entering serially, means 1 bit at a time or 1 bit in 1 clock period, right? So, what is the time period? The question is like that. Okay. Now, if the frequency is this, what is the time period? Time period T equal to 1 by 200 kilohertz, which is nothing but 5 microseconds. Okay. So 200 kilo means 5 microseconds it is. Now this is the time period. The question is not what is the time period. The question is how much time is taking for 8 bits to enter. So if 1 bit is taking this much time, we are going for a serial in shift register. Serial in parallel out or serial in serial out, whatever it is a serial input. Okay. So if the bits are entered serially, means every bit will take this much of time. So 8 bits means 8 into 5. That is 40 microseconds will be the time taken. I'll read out the question once again. 8 bits can be serially entered, means every bit is entering in 1 clock period. 1 clock period for 1 bit. Likewise. Okay. So the total time will be 8 bits. I mean, for 8 bits, 8 into 5, which is 40 microseconds. Correct answer coming is option B, which is 40 microseconds. Okay. Moving on to the 8th question. The question is from multi-vibrators. We have done a very detailed and very easy to understandable video on multi-vibrators. So, a stable multi-vibrator is dash in any state. This question is asking the condition, the state of the multi-vibrator. So, a stable multi-vibrator is dash in any state. A, stable. B, unstable. C, saturated. D, both stable and unstable and saturated. Very simple question. The name itself is stating that this multi-vibrator is stable. Means it doesn't have a stable state. It is just keep on changing its state. It is not getting stable or getting settled onto any state. So the answer is B, unstable. These type of questions also you can expect in order to just confuse you. Okay. You may be knowing the exact answer, but you may get confused while seeing the options. Okay. So a stable multivibrator is not having any state. So it doesn't have a stable state. So it is unstable. Okay. So a stable multivibrator is unstable in any state. Correct answer is option B, unstable. Now moving on to the 9th question. All logic operations can be obtained by means of dash. A, AND and NAND gate. No, we cannot realize all the logical operations using AND gate. But NAND gate, yes, it is possible. B, OR and NOR gate. Again, we cannot realize all the logical operations using only NOR gates or the combination of OR and NOR gates. C, OR and NOT gates. No, not again. D, NAND and NOR gates. Yes, it is possible to realize all logical operations using NAND and NOR gates. Actually, we have discussed about this question in a couple of videos. NAND gate and NOR gates are called universal gates. Okay, very commonly asked type of question also. Universal gates these are. And why they are called universal gates? Because we can realize any gates or any logic or everything using this NAND and NOR gates. Okay. So they are called universal gates and hence the answer is option D, NAND and NOR operations. Okay. The options is given as NAND and NOR operations. Yes, it is by doing the NAND and NOR operations, we can realize all logical operations. Okay. So correct answer is option D. Now, 10th question is a logical simplification, Boolean simplification. Simplify y equal to AB complement plus A complement plus B into C. This is a little bit difficult one. Not very difficult, but little bit difficult only. Okay. I'll write it down so that you can see it. Okay. Y equal to AB complement plus A complement plus B into C. Now while looking at the options are AB complement plus C, B AB plus AC, C A complement B plus AC complement, D AB plus A. Now how to get this form? We have a sum here and a product to that and again a product term here. Okay. Now in this bracket, what I'm going to do is I'm going to apply De Morgan's law. So if you apply A complement plus B and I'm going to apply double complement. Okay. So only then it get nullifies, right? So I'm going to apply double complement to this. We'll take the upper complement as it is and we'll perform De Morgan's in the lower complement and this expression. So A complement plus B the whole complement. It is equal to A plus B the whole complement is A complement, that will be A complement, again complement, it is A into B complement, it will be, right. So you'll get a term like A dot B complement and again there is a outer complement also. Okay, I'll put the complement as same notation. Okay. That is A plus B complement the whole complement. Right. That is, if I take the bracket expression and put a double complement to it, you will get the expression like this. A dot B complement the whole complement. Now I am going to substitute this expression like this. Okay. And I will write it in the given expression. So I will be getting A, B complement. I have changed the complement signs. Okay. I'm going to give a bar. You can use either bar or the chords. Anyway, you can use. So A, B complement plus A, B complement the whole complement into C. Okay. So this is the expression. If you put a double complement and apply a De Morgan's to that, you will get a expression like this. Now I'm going to take this A, B bar inside. That is, I'm going to distribute this plus sign. Okay. So it will be A, B complement plus C into A, B complement plus A, B complement the whole complement. Right. I hope it is clear. I have just distributed this positive sign inside. So you can also write this like this, right? There is the plus and then a bracket. And I'm going to distribute this plus inside the bracket. So here there is a product term. So if you distribute the plus sign, it will be A, B complement plus A, B complement the whole complement. That term is here. And the next term is A, B complement plus C. And then product of both those. Okay. So this will be your resultant expression. Now it is very easy. That is A, B complement plus C. And this is 1 into 1. That is this. Okay. So A, B complement plus C is your expression. And the correct answer is option A. I really hope you understood it. See, this type of questions needs practice. You need to know that in which place what logic to apply. So you have to practice it, only then you will get the trick. Otherwise, by solving any one question or two questions, you won't be able to get the trick or how to do these sort of problems. Okay, so how to identify that you have to apply De Morgan's is by practice only. Okay, so what I have done here is I have applied a De Morgan's, and before applying the De Morgan's, I have put a double complement. Double complementing means makes no effect. So just I have double complemented this bracket term and I have given a De Morgan's to the term, and one complement sign remains as it is. So that expression you are getting is A, B complement the whole complement into C again. Then the next thing I have done is I have distributed this positive sign inside the bracket. So I will get two terms and then a product of that two terms. So A, B complement plus C into A, B complement the whole complement plus this term. Okay. So this term is 1. This term you will get as. That is the answer. Okay. A, B complement plus C is your answer. So correct answer is option A. Okay. So these are the 10 questions which I will include in this video. Let's see the 10 questions. So this is a mock test for analog electronics. I hope you have seen the questions and answered the question. Now we can see the solutions. The first question is, a simple circuit diagram of serial clipper shown below. What is to transfer CARA? Okay, so the diagram I will draw it for you. There is a V in here. The question is from clippers. So if you're preparing for any competitive examinations, try to attempt these mock tests for subject wise, so that it will be useful for you to find whether you are good at that subject or you need more preparation on that subject. Okay, so this is V out. Now this is a serial clipper which is given in the question. Sometimes it won't be given. The circuit diagram will be only given to you and you have to find the cara. Okay, but here the question has the naming of the circuit also, which is serial clipper. Now the serial clipper is used to clip off some portion of your waveforms. And if you observe the connection of the diode, this is nothing but a negative clipper. Why? Because see, when the positive half cycle of the wave is coming, the diode is connected in positive and then negative. So it is forward biased. Positive of the half cycle is coming means positive of the diode is connected, and positive it is forward biased. But when the negative half cycle is coming, the diode will get reverse biased and hence it will act as an open circuit. So this is nothing but a negative serial or series clipper. We have done detailed video on series and shunt clippers, that is clippers part 1 and part 2, that you can study all these. Okay, so here we need to find what is the transfer cara. So what will be the transfer cara of the diode? In the question it is also given, use constant voltage drop across the diode. So the question is specifically saying that there is some voltage drop across the diode. So the transfer cara won't start from your origin. Okay, so the transfer cara will be in which quadrant? This is a negative series clipper. So it will clip off the negative half cycle. So there won't be any negative quadrant or negative, there won't be any signal or transfer cara in the negative quadrants. It will be only in the positive quadrants, because this circuit will clip off all the negative half cycles or the portion of the negative half cycle. And also, since there is a voltage drop across the diode, it won't start from 0. It will start after the threshold or the built-in value for your diode. That much potential drop. After that, only the diode will start conducting or the circuit will work. Okay, so this is your transfer cara. And from the options, option A is starting after VT. Here it is VT, this is V in and this is V out. Okay, so this much, after this much delay or this much drop across a diode, it will conduct. Okay, so then that much portion of the wave you will be getting. There won't be any waveform in the negative. Why? Because it is a series clipper clipping off negative half cycles. I hope these are the basics of clippers, and also clampers are important. Okay, so the correct answer here is option A. So this is the transfer cara of this negative series clipper. Okay, moving on to the second question. Analog electronics is a very important subject, especially for competitive examination. A lot of questions can come from various areas. Okay, so please to prepare it very thoroughly. Try to practice maximum questions so that you can score maximum. Next question. In a diode, the change in voltage being applied across it is 2 volt. Okay, so the change in voltage applied across the diode is 2 volt. The change in minority carriers outside the depletion region is 1.2 into 10 raised to minus 8. Find the diffusion capacitance. The question is regarding diffusion capacitance, or CD, that is equal to dq by dV. Change in charge by change in voltage. We know that Q is equal to CV. So that equation we are using as a change. Diffusion capacitance means due to the concentration variations, diffusion capacitance is happening, right? So change in charge by change in voltage. What is a change in charge? It is 1.2 into 10 raised to minus 8. That is a change in carriers, minority carriers. By change in voltage is 2. So that is 6 nanofarads. Correct answer is option D, 6 nanofarad. Okay, you have to adjust the decimal and the 10 to the powers. It will be 10 raised to minus 9. Okay, so then 6 into 10 raised to minus 9 or 6 nanofarads is the answer. Correct answer is option D is the correct answer. Moving on to the third question. Third question, consider the following circuit where the transistors are similar silicon transistors. Given I1 equal to 2 ampere, I2 equal to 1 microampere, VCC is equal to 12 volt. Find the value for R2. Okay. So you need to find the value for R2. R2 is a resistor connected to the Q2 transistor. Okay. So R2, if you see, I'll draw the circuit for you. There is a VCC, there is a resistance value R2, there is this transistor Q2, it's grounded. If you have seen the amplifiers video, this is current mirror. Okay, so this is a current mirror circuit actually. This is I2. Okay, this is R1, this is Q1. Yeah, this is Q1, this is R1, this is Q2, this is R2. The current here is I1, right? This is VCC, this is R2. You need to find what is the value for R2. Now, if you see R2, it is connected to VCC, one part, and one portion is connected to the base emitter region, right? So, the voltage drop across the R2 will be VCC minus VBE will be the voltage drop, right? You don't need the voltage drop. Write it below. Okay, so I'll write it here. So VCC minus VB will be the voltage drop across the resistance, since it is connected in this area, one end to VCC, one end to VB portion. So it is VCC minus VB. Now you need to find R2. So R2 is voltage by resistance. Sorry, voltage by current. Current is I1 is the current, which is clearly seen in the figure. So I1 is the current flowing through it. And the value of I1 is also given 2 milliamperes. So just substitute the values and find the value for R2. So it will be VCC is 12, right? So 12 minus 0.7. Since it is given that both the transistors are identical silicon transistors, VB will be 0.7 only. I1 is 2 milliamperes. If you solve it, you will get the value as 5.65 K, right? This will be your value for R2. Correct answer is option D is the correct answer, which is 5.6 kilo ohms. This is option D. Okay. Correct answer for this question is R2, which is 5.6 K ohms. This is the answer for your third question. Moving on to the fourth question. There's a lot of current mirror type questions, theory questions, and also numericals. Okay. Fourth question is from tunnel diode. Tunnel diode can be used as an active device because that. So this is one important property for tunnel diode. Generally, while discussing diodes, they are passive devices. They don't amplify the signal or anything. They just act as switches, right? But tunnel diode, a specific or speciality of a tunnel diode is that they can act as active devices. Now, why tunnel diode act as active devices is a question. A, its negative resistance region is used. B, it conducts at a faster rate. C, it triggers the flow of electrons in reverse bias. No, we don't use, while discussing tunnel diodes, we don't give importance to reverse bias condition because it don't work in reverse bias. D, of tunneling effect. Because of the tunneling effect. The answer is because of the negative resistance region. There is negative resistance region. In negative resistance region, they act as active devices. Okay. And the VI cara of the tunnel diode is actually falling into the first and the second quadrant. Okay. So the answer is because of the negative resistance region. Again, we have done a detailed video on tunnel diode also. In that, I've explained about the cara, the negative resistance region, peak current, peak voltage, valley voltage, all those things we have discussed. So due to this negative resistance property, negative resistance region present in the tunnel diode operation cara, it can act as an active device. Correct answer is option A. Fifth question. Okay, fifth question is from rectifiers. If input frequency is 50 Hz, then ripple frequency of a half wave rectifier is dash. So I'll draw the input and output waveform of a half wave rectifier. Half wave rectifier, if this is the input, normal a sine wave or an AC is given, the output will be like this. Oh, sorry. Okay, just positive half cycles only. Okay. This will be your output. Right. Now, if this is one frequency cycle, it is passing only one half of the cycle, right? That is, the frequency is exactly same, right? But for the full wave, if this is one cycle or one frequency cycle, it will be passing two half cycles for a full wave rectifier. So here the question, I don't want to confuse you. See, the question is, what is the ripple frequency of a half wave rectifier output? If the input frequency is 50 hertz, the output frequency is exactly the same, because in this cycle the full wave is passing over one wave or one cycle. The frequency will be exactly same. Here also one half is passing. So the rectified version also, the frequency is exactly the same. Okay. So F is equal to 50 hertz will be the ripple frequency also. I'll read out the question once again. If input frequency is 50 hertz, then ripple frequency of half wave rectifier is same. Ripple frequency is 50 hertz itself. Answer is option B. So why? Because here also one cycle is passing. This is the one cycle of the rectified output, right? So this is also one cycle during the frequency period. Okay. So this is same frequency as your input. The output frequency will be same as input only. Okay. So correct answer will be option B, 50 hertz. Moving on to the sixth question. Consider the circuit. Yeah, I'll draw the circuit for you. Okay. The question is, loading occurs when? Okay, this question is from cascaded amplifiers. A1, there is a resistance of value R1. There is again resistance of value R2, cascading with A2. This is V in, this is V out. Now, when do cascading occurs? Sorry, the question is, when do loading occurs? The loading means some of the noise coming or some of the variations happening at the input side. Okay. So the options are A, R2 is small, B, A1 is small, C, R2 is large, D, A2 is large. So the loading occurs when the input resistance is less. Okay. Please note this thing. Loading or some noises coming or some variations happening when the input resistance is less, then it allows some noises or some fluctuations to the input side. This is called loading effect. Okay, so when R2 resistance is less, then there will be loading. Okay, correct answer is option A, R2 is small. Because there is only one input resistance in this figure. This is not an input resistance. This is an output resistance. This is the input resistance of A2. And when its value is less, there can be some loading effect from this stage. Cascading of amplifiers means cascading of various amplifier stages. So when the R2 is not sufficient enough to avoid some variations or some loading effects from this stage to the next amplifier stage, which is on the A2 side, then loading occurs. So R2 should be large enough to prevent loading. And when R2 is small, loading occurs. Very simple, right? I hope it is clear. Correct answer is option A. Moving on to the seventh question. Seventh question is from Hartley oscillator. Which component of the Hartley oscillator is used in feedback system? We have done a detailed video on oscillators. Very quick, revisable, easy, simple video, to the point video. Okay, so you can see that for reference. It is again in the analog electronics playlist itself. So, which component of Hartley oscillator is used for feedback? A. Inductor, B. Resistor, C. Capacitor, D. Transistor. Correct answer is A. Inductor. If you see the structure of the feedback unit of a Hartley oscillator, there is a inductor combination. Okay. So, correct answer is A. Inductor. Theory question. This is direct question. Okay. Now, moving on to the 8th question. The 8th question is, find the power rating of the diode in the circuit when VZ is equal to 5 volt. I wrote the circuit for you. This is a Zener diode circuit. Zener diode is a very important area. So there is a Zener diode here. And there is a load 400 ohms. This is 200. This is 5 volt Zener. That is VZ is equal to 5 volt. And this is 15 volt. Now you need to find the power rating. How to find a power rating of a circuit is by removing of the load. So you have to remove this load for finding the power rating. Now what is the current flowing through this Zener? Now this is a series circuit now. The voltage, this is the current. Consider that this is the current and call it as IS. Okay. Whatever current is passing through 200 ohm will be the same as that of the current passing through the Zener, because they are connected in series now. Okay. There is no current division happening because we have removed the load. Okay, so the current passing through the resistance will be now 15 minus 5. That is this voltage minus voltage drop across the diode by 200. Right. So that is the current passing through the resistance. That is IS. We have called it as IS. So 15 minus 5 by 200 is equal to 50 milliamperes. Right. So 50 milliamperes is the current passing through the resistance, and that is the same value of current passing through the Zener diode also. So IZ is equal to IS is equal to 50 milliamperes now. Now we don't need current, we need the power rating. What is power equation? Power P equal to VZ IZ. That is VZ is 5 volt. 5 into 50 milliamperes will be 250 milliwatt. Okay, 250 milliwatt will be the power. Correct answer is option C. 250 milliwatts is the power rating. Now in order to find the power rating of any circuit, you have to remove the load and see the power generated in the circuit. Here the power is VZ IZ, that is there is power generated across a Zener, that will be the power rating. Okay, so here answer is 5 into 50 milliampere, that is 250 milliwatts, which is option C is the answer. Okay, so here this is a voltage regulator circuit. So the Zener is acting as a regulatory unit. So the power rating is the power generated across a Zener. You have to find. Okay, so this will be 250 milliwatts, which is option C. Moving on to 9th question. Assume the diode in the given circuit diagram to be a silicon PN junction diode. What is the current for the given circuit diagram? Okay. So this circuit is having a voltage source of 5 volt, 1K resistance and diode D1. Now what will be the current through this diode is a question. Very simple. You have to just see the polarity of the voltage source and the diode. This is positive and negative. This is negative and positive. So the diode is in reverse bias condition and it acts as an open circuit. What is the current? I equal to 0. There is no current generated. You don't have to also there is no voltage drop across a Zener is not also given. In that way also you cannot find the current actually, but even if the voltage across a diode is also given, the diode is connected in a reverse bias condition. So the current has to be 0, because in reverse bias condition normal diodes will act as open circuit, right? So the current will not flow since it is an open circuit. Correct answer is option B. 0 is the correct answer. 10th question is a numerical question from multivibrators. Given that the feedback factor of an stable multivibrator is 0.3. So the beta feedback factor of an stable multivibrator is 0.3. Find the frequency of the output. You need to find what is the frequency of output. Okay, so first we'll write the equation for time period. Time period T equal to 2RC ln 1 plus beta by 1 minus beta. This is equation for an S-stable multivibrator. Time period for an S-stable multivibrator. So 2 RC ln 1 plus beta by 1 minus beta. What is beta? Beta equal to 0.3. So it will be ln 1 plus 0.3 by 0.7. This 1 minus 0.3 is 0.7. This will be 1.3. Okay, ln 1.3 by 0.7. And what is the value of R and C? The circuit diagram is having a C equal to 4 microfarads and R equal to 10K. Okay, so if you see the feedback circuit, I'll draw the circuit for you. So the circuit is having a 4 microfarads here. There is a feedback resistance of 10K. Okay, this is the feedback resistance. And this, there is a resistance here. And here there is again another resistance. The values of that resistance is not given and so it is not required. So this is acting the feedback unit. Okay, so R is 10K. C is 4 microfarad, right? So you have to substitute R as 10K and C as 4 microfarads and from this diagram and then solve this to find the T. Okay, now I'll remove it. That is 2 into R is 10K, 10 into 10 raised to 3 into C is 4 microfarad, 4 into 10 raised to minus 6. Then ln 1.3 by 0.7. Okay, and if you solve it, you will be getting the T equal to 49.52 milliseconds. Solve for this sum and you will be getting 49.52 milliseconds. And then F will be 1 by T, right? And the value you will be getting is approximately 20 Hertz. Correct answer is option C. Okay, so these are the 10 questions which I have included in this video. I really hope that this video will be useful for you because analog electronics is very important, especially. Hello and welcome to EC Electronics. So in this video, we are going to see the MCQ questions from transistors topic. The transistors topic is very important. A lot of twisted type of questions can come from this area, even though it sounds very simple. Okay, so you have to really prepare in depth from this topic. Okay, so this video I'm doing especially for the AFCAT exam preparation, which is going to be happen in the next month. Okay, I've tried to include variety of questions from this area of transistors. Okay, now let's see the 10 questions. So this video is an MCQ video for transistors. Okay, so I hope that you have seen the 10 questions. Now we are going to see the solutions. You will be seeing the questions on board. Okay, so the first question is, the current amplification factor beta is given by dash. A, IC by IB, B, IB by IC, C, IE by IB, D, IB by IE. So what is current amplification factor beta? So beta is the common emitter current amplification factor. So the emitter will be common. The input is applied to the base. The output we are going to take from the collector. Okay. So current amplification factor means how much the current is getting amplified. So in order to find the current amplification factor, you have to take the output current ratio to input current. That is the output current to input current. That ratio will actually give you the current amplification factor, or by what percentage the current is getting amplified. So here clearly the output terminal is collector and the input terminal is base, since it is a common emitter configuration. So output current is IC, input current is IB. And this is the beta, which is the current amplification factor for common emitter configuration. Okay, so from the options, correct option coming is A, which is IC by IB is the current amplification factor beta, its value. Okay, so the first question, correct answer is option A. Now moving on to the second question. The second question is, when the signal is applied, the ratio of change in collector current to the ratio of change in base current is called dash. A, DC current gain. B, base current amplification factor. C, emitter current amplification factor. D, AC current gain. The correct answer is AC current gain. Why? Because we are going to apply a input signal, right? So when there is an input, it is called a AC current gain. So the AC current gain is actually given by beta here. For earlier case, we are not considering any signal applied. Okay. But here we are going to apply a signal, and in that case, beta will be delta IC, change in the input, change in the collector current to change in the base current. So when the signal is applied, it is called AC current gain. Okay. So the correct answer is option D. AC current gain will be the ratio. That is the delta IC to delta IB is now, it is the AC current gain. Okay. So moving on. Okay. So the third question is, the relation between alpha and beta is dash. So this question is asking the relation between two current gains, alpha and beta. So the options are A, beta equal to alpha by 1 plus alpha. Option B, alpha equal to beta by 1 plus beta. C, beta is equal to 1 by 1 plus alpha, and D, none of this. Okay, so you should be knowing the relation between the three current gains. There are three configurations of the transistors: common emitter, common base, and common collector. And for common emitter, the current amplification factor or current gain is given by beta. For common base, it is alpha, and common collector, it is gamma. Now the relation between these three, you should be knowing that beta is equal to alpha by 1 minus alpha, and alpha is equal to beta by 1 plus beta, and gamma is equal to 1 plus beta. So these are the three current gains and the relations between them. Okay, so here the question is connecting these two factors, that is alpha and beta, and you have to find the relation between alpha and beta, which is alpha equal to beta by 1 plus beta is the relation. Okay, so you should be knowing these three columns, the current gains and the relation between them. It is very important. So the correct answer is alpha equal to beta by 1 plus beta, which is option B, is the correct answer for your third question. Moving on to the fourth question. So the fourth question is connecting to the mode of operation or the region of operation of the transistor. When the collector junction is reverse biased and the emitter junction is forward biased, the operating region of the transistor is called dash. Okay, so based on the forward bias and the reverse bias of the two junctions, the transistor configuration can be of 4 types. Okay, so there are two junctions, emitter base junction and collector base junction. Okay, so EB is emitter base junction and CB is collector base junction. Now we'll discuss the mode here in this column. So first one, when the emitter base junction is forward bias and the collector base junction is reverse bias, the mode is called active. These are actually very basic things. Anyway, very important for the exams. Now, when the emitter base junction is forward bias again, collector base junction is also forward bias, means it is called saturation state. Okay. Now, third case, when this reverse happens, when the emitter base is reverse bias and the collector base is forward bias, means it is called reverse active. Last case, when both the junctions are reverse bias, we call it as saturation state. Sorry, it is called cutoff state. Cutoff. So these are the 4 modes of the transistor, or 4 regions of operation of the transistor based on the biasing of emitter base and collector base junction. Now in this question, when the collector junction means collector base junction, is reverse biased and the emitter base junction is forward biased, means it is a first condition given in the reverse form. First this is given, then this is given. Anyway, the mode or the region of operation is active region. Okay, so the correct answer is option B, which is active region. It is not inverted or cut off or cut in region. It is active region, which is option B. Okay, so moving on to the 5th question. So the 5th question is, the input of a common base transistor is given between dash. Common base transistor, where we are going to give the input. Collector and emitter terminal A. B. Base and collector terminal. C. Ground and emitter terminal. D. Emitter and base terminal. Okay. So this is a common base. So this is the base. Base is common. Input is going to be applied to emitter, or input terminal we say it is emitter. Collector is the output terminal. Now where we are actually going to apply the input is in between the emitter and the base terminal. Okay. So the correct answer is option D. In between the emitter base terminal, we are actually going to apply the input. Okay. But if somebody is asking you what is the input region, or in the input terminal, it is emitter. Output terminal is collector. So we are going to apply the input between actually these two, emitter and base. So the correct answer is option D, emitter and base terminals. The 6th question. The 6th question is, the current gain of the common base transistor is dash. So it is asking about the value of the common base current gain. A. Less than or equal to unity. B. Equal to unity. C. Greater than unity. D. Remains the same. Okay, so there is a formula revision video of transistors. In that, I have discussed about the regarding the current gain, voltage gain, the impedance, and its comparison between the 3 configurations: common emitter, common base, and common collector. Okay, so the table I have explained in that video. So please do watch it. It is in the analog electronics playlist. Okay, so here the question is asking the value for current gain of a common base transistor. So for a common base transistor, the current gain will be less than or equal to unity. Okay, so the correct answer is A, less than or equal to unity will be the value for the common base current gain. Correct answer is option A. Moving on to the 7th question. The 7th question is, the input characteristic of a common base transistor resembles dash. A. Forward bias diode. B. Illuminated photodiode. C. LED. D. Zener diode. So if you draw the input chara of a common base transistor, it will have the resemblance to which of these? That is a question. Forward bias diode, or illuminated photodiode, or C. LED, or D. Zener diode. The correct answer is, the input chara resembles to that of a illuminated photodiode, and the output chara, it resembles to that of a forward bias diode. Okay, so just note it down. The input chara resembles to illuminated photodiode. and the output gara resembles to forward biased diode, normal diode. Okay, so that is the case for input gara and output gara. Here it is asking input gara, so correct answer is option B. Moving on to the 8th question. So the 8th question is, the small amount of current which flows even when base current IB is 0 is called dash. IBEO, that is the first option. Option B, ICBO. Option C, ICEO. Option D, IC. So the correct answer is ICEO is the minor current or the small amount of current which is flowing even when the base current is equal to 0. Okay, so you can write the collector current, total collector current will be equal to beta times IB plus ICEO. This is the relation. Okay, so even when the current IB is equal to 0, there will be some minority current ICEO. Okay, that will constitute to the total collector current. So the question is asking about the small amount of current, which is nothing but ICEO is the small amount of current flowing. Okay, so the correct answer is option C. Okay, then 9th question. The 9th question is, in a PNP transistor operating in active region, the main stream of current is dash. A, drift of holes. B, drift of electrons. C, diffusion of holes. D, diffusion of electrons. So, for a PNP transistor in active region, the main stream of current is actually due to the diffusion of holes. Okay, so since it is a PNP transistor, it is holes, and since it is in active region, the main contribution will be due to the diffusion. Okay, so since we are applying the external potential, there will be diffusion happening. So there is since the major carriers are holes in a PNP, it will be diffusion of holes. Okay, so the correct answer is option C, diffusion of holes. 10th question. In which region a transistor acts as a closed switch? So this is very important. You should be knowing that when the transistor is acting as a closed switch and when the transistor is acting as an open switch. Because transistor has a very important property that it can act as a switch. So, in which region transistor acts as a closed switch? A, cutoff region. B, inverted region. C, active region. D, saturated region. Correct answer is, when the transistor is in saturated region, it acts as a closed switch. And when it is in cutoff region, it acts as an open switch. Okay, so when it is in saturation region, it acts as a closed switch. And when it is in cutoff, it acts as a open switch. So in order to close and open the switch, we have to shift between these two regions. Okay, so the saturation region, it will act as a closed switch, and in cutoff region, it will act as a open switch. So these two things is also very important, because transistor as a switch is a major topic. Okay. Hello and welcome to EC Electronics. So in this video, we'll be seeing the MCQ questions for Zener diodes. And this MCQ question video we are doing as a mock test. First, you will be seeing the questions, then the solutions. So this video is an MCQ video on Zener diodes. So you have already seen the 10 questions. Now we are going to see the solutions of the 10 questions. I've tried to include maximum more theory questions in this video because we have already done 2-3 videos on the Zener diode numericals. So if you are focusing on studying the numericals, please do watch that video. Okay, so here we'll be discussing more concepts. So the first question is, you'll be seeing the question on board. What is the level of doping in Zener diode? A. Lightly doped. B. Heavily doped. C. Moderately doped. D. No doping. So this question is asking about the level of doping of a Zener diode. So a Zener diode is heavily doped so that the breakdown voltage occur at the lower voltages. For lower applied voltages, in order to have breakdown, the Zener diode is actually heavily doped. Okay, so the correct answer is option B, which is heavily doped. So you should be knowing a Zener diode is a heavily doped diode. Okay, so why the heavy doping is to ensure that the breakdown is happening quickly. The second question, the depletion region of a Zener diode is dash. So question is asking about the thickness of the depletion region. A, thick, that is the depletion region is thick. B, normal. C, very thin. D, very thick. The correct answer is option C, very thin. Okay, so since this diode is mainly focusing on breaking down of the junction, the depletion region is actually very thin. The correct answer is option C. So the Zener diode is fabricated by heavily doping of both the sides, that is both N and P sides of the junction, and this heavy doping results in an extremely thin depletion region. So the correct answer is C, very thin. Okay. Third question. The third question is connected to the electric field intensity. The question is, the electric field required for field ionization is of what order? Okay, so in a Zener diode, very high electric field is produced for even a very small voltage. Okay, so for even very small applied voltage or input voltage, there is a high electric field is produced. So this electric field is actually required for the field ionization, and its order is 10 raised to 6 volt per meter. The unit of electric field is volt per meter, right? So the electric field produced is of the order 10 raised to 6 volt per meter, that is mega. Okay, so the correct answer is option C. So just know that even if we apply very small voltages, a high electric field is actually produced for field ionization. Okay, so correct answer is option C, 10 raised to 6 volt per meters. Moving on to the next question, which is the fourth question. The question is, a Zener diode when biased correctly, I'll read out the options. A, never overheats. B, has a constant voltage across it. C, act as a fixed resistance. D, has a constant current passing through it. Correct answer is has a constant voltage across it. Why? Because this property is making the Zener diode use as a voltage stabilizer. So the most common use of Zener diode is to produce a stable voltage or to use as a voltage regulator. And when this diode is biased properly, it will produce a constant voltage across it. Okay, so this is the stabilized voltage, or in order to stabilize a circuit voltage, we actually use this Zener diode. Okay, so the correct answer is option B, has a constant voltage across it. B, has a constant voltage across it is the correct answer for the fourth question. The fifth question is, fifth question, which of the following is true about the resistance of a Zener diode? Okay, so question is connected to the resistance. A, it has an incremental resistance. B, it has a dynamic resistance. C, the value of the resistance is inverse of the slope of IV cara of the Zener diode. D, all of the mentions. All the statements are correct. It has an incremental resistance. This resistance is dynamic in nature, and also the resistance is inverse of the IV cara. Yes. So the correct answer is option D, all the mentioned. And also we have done a quick revision video on Zener diodes, in which we have explained about all the important concepts of Zener diodes. And in that video, towards the end also, I have included some MCQ type of questions. So if you want to have a quick revision of the concepts of Zener diode, please to watch that video. Okay, how the Zener diode is working, what is the forward bias condition, what is the reverse bias condition, how the voltage stabilization is done. All those things I have included in the quick revision video. Okay, so please do watch that video. Then, sixth question. Okay, this is sixth question. I'll remove it. Sixth question is, Zener diode is designed to specifically work in which region without getting damaged? A, active region. B, breakdown region. C, forward bias. D, reverse bias. The correct answer is B, breakdown region. So the other name of Zener diodes is breakdown diodes. Okay. So the Zener diode has a breakdown property, or it is working properly in the breakdown region. So the Zener diode is specifically designed to operate in the breakdown region without getting damaged. Because of its characteristics, it can be used as a constant voltage device also. That is a voltage regulating device also. Okay. So correct answer here is option B, which is breakdown region. So it will work properly in the breakdown region without getting damaged. Correct answer is option B. Seventh question is a numerical type of question. There is a circuit given. You can see the question on board. So the seventh question. What is the output voltage is the question. So what all things have been given? I'll draw the circuit for you. There is a resistance, which is a series resistance. There is a Zener diode, a load. The value of the load is 10K. The value of R is 5K. The value of this Zener voltage, that is VZ, is equal to 50 volt. Then applied voltage is 120 volt. We need to find what is the V out. So the V out, so here we need to find the output voltage. The output voltage is nothing but the voltage across the load resistance. So first we will consider that there is no Zener diode connected in the circuit, and we will find the open circuit voltage. So just apply the voltage division rule, 120 into 10K by 10K plus 5K, and you will be getting the voltage as 80 volt is the open circuit voltage. Okay, that is 80 voltage is coming across this branch, that is 10K branch. So same as the voltage will be coming across the Zener diode also. So this Zener diode is getting sufficient voltage, sorry, it is 50 volt. So the Zener diode is getting sufficient voltage to undergo breakdown. What is the breakdown voltage? VZ is equal to 50 volt. That is minimum 50 volt it requires to undergo breakdown. So when it is undergoing breakdown, there is a constant voltage drop. Here there is sufficient voltage, 80 voltage is coming. So it will undergo breakdown, and we know that due to the property of a Zener diode, when it undergoes breakdown, there will be a constant voltage drop across it, which is equal to 50 volt. And which will be the same voltage coming across the load resistance also, since they are connected in parallel connection. Okay, I hope it is clear. So first we have to check whether the Zener diode is getting sufficient voltage to undergo breakdown or not. So for that we will apply the voltage division, and we will find the voltage coming across these terminals. Okay. So there is 80 voltage coming, which is sufficient. So the Zener will undergo breakdown, and hence the voltage across the 10K will get stabilized to 50 volt. So the correct answer is A. 50 volt is the voltage across this load resistance. So this is a voltage stabilizer circuit. and the Zener diode is acting as a voltage stabilizing entity or element. And due to the breakdown property of the Zener diode, when it undergoes breakdown, there is a constant voltage drop, right? That is nothing but Vz, which is equal to 50 volt, same as here also. Okay, correct answer is option A, 50 volt is the correct answer for the 7th question. Moving on to the 8th question. The 8th question is, which of the following is true about the temperature coefficient or TC of a Zener diode? A. For a Zener voltage less than 5 volt, TC is negative. B. For Zener voltage around 5 volt, TC can be made 0. C. For high voltages of Zener diode, TC is positive. D. All the mentioned. Okay. So, for generally, Zener diode has positive temperature coefficient of resistance, whereas normal diodes have negative temperature coefficient. Okay. But here the statements given are for lesser voltages, TC is negative. Less voltages than 5 volt, TC is negative. And also for voltage around 5 volt, TC is 0. For higher voltages, TC is positive. And D, all the mentioned. So the correct answer is option D, all the mentioned. All the answers or all the options are correct only. Okay. Moving on to the 9th question. Ninth question is, Zener diode can be effectively used in voltage regulator. However, these days being replaced by more efficient dash. That is, generally we use Zener diodes as voltage regulators, but nowadays these Zener diodes are replaced by some other element. What is that? A. Operational amplifier. No, we cannot use operational amplifier for voltage regulating purpose generally. B. MOSFET. C. Integrated circuits. D. None of the mentioned. Correct answer is option C. Nowadays we are using ICs or integrated circuits for voltage regulating purpose rather than using Zener diodes. Okay, so correct answer is option C. 10th question. The question is, a 9.1 volt Zener diode exhibits its nominal voltage to a test current of 28 milliampere. At this current, the incremental resistance is specified as 5 ohm. Find VZ0 of the Zener model. So what all things have been given? The test current is given. Test current is given 28 milliamperes. Then Vz is given 9.1 volt. Then R value is given, which is 5 ohm, which is a incremental resistance. Okay. We need to find Vz0. Okay, so the equation is Vz, Zener voltage Vz is equal to Vz0 plus the test current into the incremental resistance. Test current into R, which is the incremental resistance. Test current is 28 milliampere into 5. So 28 into 10 raised to minus 3 into 5. And here we also know Vz, which is 9.1. So while solving, you'll get Vz0 equal to 8.96 volt. So the Zener diode, this is actually a Zener diode model. We are going to apply some test current with some incremental resistance, and the Zener voltage will vary according to this values. But first we need to find the initial Zener voltage, and which will get actually affected or which will get modified to produce the final Vz, right? So we need to find actually that value Vz0, that is 8.96. And this will get increased due to the test current and the incremental resistance combination. So this is actually a Zener model circuitry. Okay. So you'll be getting Vz0 as 8.96 volt. So that is the question. So this video is an MCQ video of op-amp. We have already seen the 10 questions. Now we are going to see the solutions of the 10 questions. So these videos I'm doing especially for the AFCAT exam preparation, which is going to happen on the first week of October. Okay. So the first question is, you'll be seeing the questions on board. Which of the following electrical characteristics is not exhibited by an ideal op-amp? So the ideal op-amp CARA, there are various CARAs. All the CARAs are very important, especially if you're preparing for competitive examinations. You should be knowing all the CARAs because they'll be either giving in the options like pick out the correct CARA of an ideal op-amp, or they'll be giving various CARAs out of which you have to pick the wrong one. Okay. So any of these type questions can come. So the options are A, infinite voltage gain. Yes, they are having infinite voltage gain. B, infinite bandwidth. C, infinite output resistance. D, infinite slew rate. Okay, so the correct answer is option C. That is, infinite output resistance is actually a wrong option. Because for an ideal op-amp, the ideal op-amp should have zero output resistance. Why? Because in order to have maximum connections to the device, that is, the output should be connected with maximum number of device, or the output can drive maximum number of device. For that purpose, we have made the output resistance is 0 and the input resistance is infinity. So if the question is like, or if the option is like input resistance is infinity, means it is right. But the output resistance is not infinity, it is 0. Okay. So here the question is asking about the wrong CARA or the wrong option, which is option C. Okay. So moving on to the second question. The second question is, an ideal op-amp requires infinite bandwidth because dash. A, signals can be amplified without attenuation. B, output common mode noise voltage is 0. C, output voltage occurs simultaneously with input voltage changes. D, output can drive infinite number of devices. The options are almost all correct, but the question is connected with the bandwidth. Why an ideal op-amp need infinite bandwidth? Because the op-amp can amplify the signals without attenuation. In order to have maximum amplification without any attenuation, it is being designed with infinite bandwidth. Okay, so correct answer is A. Since it want to amplify the signals without attenuation, it requires high or infinite bandwidth. Okay, so the second question's correct answer is option A. Moving on to the third question. So the third question is, how will be the output voltage obtained for an ideal op-amp? A, amplifies the difference between two input voltages. B, amplifies individual voltages, input voltages, means amplifies individual input voltages. Okay. So C, amplifies product of two input voltage. D, none of the mentioned. So this op-amp, we also call it as differential amplifier. It is taking the difference between the inputs. So there will be, if you draw the structure of an op-amp, there is an inverting terminal, there is a non-inverting terminal, and we will be applying two voltages to this terminal, and there will be some gain of the op-amp. So what it takes is taking the difference. So the op-amp is always interested in the differential mode. It is not interested in the common mode. Okay. So the differential voltage it is taking. So it is taking the difference between these two voltages and then it amplifies. So that is the basic difference between any other type of amplifier or the other amplifiers and op-amps or operational amplifiers. That's why we call it as differential amplifiers also. So it is interested in the difference between the two input voltages. Okay, so correct answer is A. That is, it amplifies the difference between two input voltages. So, fourth question. So the fourth question is a small numerical question. Find the input voltage of an ideal op-amp. It's one of the inputs and output voltages are 2 volt and 12 volt. And in bracket, it is given that gain equal to 3. Now, what is the equation for the output voltage? V out is equal to gain into V in 1 minus V in 2. So these are the two inputs. It is not given that whether the one input is to positive terminal, one input is to negative. Just it is given that one of the inputs is 2. The other input we need to find. Also, we have been given the output voltage and gain also. So you have to substitute in this equation, and 12 is equal to 3 into 2 minus V in 2. Okay. So there are actually two inputs here, out of which one is given and the output value is also given and gain is also given. So you need to find the next input. So from this you will be getting 4 equal to 2 minus V in 2, or you will be getting 2 minus 4 equal to V in 2, that is equal to minus 2 volts. Okay. So by just applying into this simple equation, because none of the other specifications is given, we can use only this equation. Okay. So correct answer is minus 2 volt, which is option D. Okay. Fourth question, correct answer is option D. So fifth question. So the fifth question is, which factor determines the output voltage of op-amp? A, positive saturation, B, negative saturation, C, both positive and negative saturation voltage, D, supply voltage. Correct answer is option C, both positive and negative saturation voltages. Okay, so the output is proportional to the input voltage only until it reaches a saturation voltage. So the output cannot actually exceed the positive saturation voltage and also negative saturation voltage. It cannot exceed. So your output can either be positive or negative, but it cannot exceed both of these saturation voltages. Can be also positive, also negative. So both these voltages or both these values are very important. It determines the output of your op-amp. Okay. So the factor which determines the output voltage of op-amp is actually option C, both positive and negative saturation voltages. Fifth question, correct answer is option C. Okay. Sixth question. So the sixth question, a figure is given. Determine the output of the following circuit. Okay, I'll draw the circuit for you. Anyway, you can see it on board. There is an inverting terminal, there is a positive which is non-inverting terminal. There is V2, and to the V2 you are going to connect your input signal. So V2 is the input signal, and also the value of V1 is not given, so we cannot really assume about any voltages being connected to that. It is given that a input signal is connected to the inverting terminal, that is V2. Now V out is equal to dash. It is the question. Options are A, 180 degree in phase with input signal, B, 180 degree out of phase with input signal, C, same as that of input signal, D, output signal cannot be determined. So this is this configuration in which you are going to connect your input signal to the inverting terminal is called inverting amplifier. If the input is connected to inverting terminal, you call it as an inverting amplifier. Whereas if it is connected to a positive terminal, it is called non-inverting amplifier. Okay. So these are basic amplifier configurations of op-amp, and also we have discussed about this op-amp configurations in the op-amp quick revision video. Okay. So you can have a look if you want to. So the input is connected to the inverting terminal. So it is an inverting amplifier. And the most important characteristic of a inverting amplifier is that your output signal will be inverted with respect to the input signal. That is, it will be inverted by 180 degree. That is, it will be 180 degree out of phase with your input signal. Okay, so that is one important cara of the inverting amplifiers. Whatever you are going to give to the input side or in the inverting terminal, whatever signal you are going to connect, you will get an output 180 degree out of phase. Okay, so correct answer here is option B, which is 180 degree out of phase with the input signal. You are not being given the value of input signal, you have just been asked the theoretical concept. Okay, so you have to answer like it will be 180 degree out of phase with the input signal. So correct answer is option B. Now, next question, which is the 7th question. The question is, how does the open loop op-amp configuration classified? This is, how can we classify the open loop op-amp configuration? A, based on output obtained. B, based on input applied. C, based on amplification. D, based on feedback network. So generally we are going to classify the op-amp, which is in the open loop configuration, by the nature of input. So not the nature actually, but to which of the terminals we are going to apply the input. Whether you are going to apply input to the positive terminal or to the negative terminal. So these are actually the classifications of open loop op-amp configurations. Okay. So the open loop configurations are actually classified according to the number of inputs and the terminal to which the inputs are connected. Okay. So it is actually depending on the input applied. So correct option is option B, based on the input applied. Next question, which is the 8th question. So the 8th question is, find the output of inverting amplifier. A, V out equal to A V in. So we have just now explained about the inverting amplifier, and we have said that your output will be 180 degree out of phase. Right. So the option A is giving V out equal to A V in, which cannot be the right answer. Why? Because they are both in phase. Okay. Then option B is the correct answer, where V out equal to minus of A V in. Okay. So these two signals, here it is, if the signal is positive, then it is giving a negative sign to make sure that these two signals, that is V out and V in, will be 180 degree out of phase. So this negative is actually indicating that your output is 180 degree out of phase with your input. Okay. So correct answer is option B. So I hope it is clear that you have to take your input and you have to multiply it with the gain, and there is a negative indicating that the output is 180 degree out of phase with the input. Okay. So correct answer is option B. Moving on to the 9th question. Ninth question is, open loop op-amp configuration has dash. A, direct network between output and input terminals. B, no connection between output and feedback network. C, no connection between input and feedback network. D, all of the mentioned. So the correct answer is, when an op-amp is in open loop configuration, you are just going to apply your input to the input side and you will be getting an output. There is no feedback or any connection to the feedback or anything. So there is a direct network between the input and the output terminals. So that is a very basic explanation of a op-amp open loop configuration. Okay. So correct answer is option A. So when op-amp is in open loop, means you are going to apply inputs here. You will be taking the output here. V1, V2 here. You are taking the, so this is plus VCC, this is minus or supply voltage plus and minus. Okay, so you'll be getting output here, you are going to apply input here. So there is a direct network. There is nothing like feedback or any feedback connection here. Okay, so correct answer is option A. The last question, which is the 10th question. The 10th question is, why open loop op-amp configuration are not used in linear applications? A. Output reaches positive saturation. B. Output reaches negative saturation. Output switches between positive and negative saturation. D. Output reaches both positive and negative saturation. So we all know that there is a positive saturation value for op-amp and there is a negative. There are positive and negative saturation values. So when operated in the open loop, what happens is your output switches between the positive saturation and the negative saturation. So since it is switching between positive and negative saturation values, you cannot use this open loop configuration for the linear applications. Okay, so that is the reason. It is switching between the positive and negative saturation levels. So correct answer is option C. The op-amp switches between the positive and negative saturation levels in the open loop configuration. So it cannot be used for the linear applications. Okay, so 10th question, correct answer is option C. So these are the 10 questions which I have included in this video. Hello and welcome to AC Electronics. Today's video is a mock test of electronic devices and circuit subject. So I've tried to include a lot of different questions from various areas. There is a lot of important areas from this subject: BJT, MOSFET, tunnel diodes, Zener diodes, a lot of devices, and the characteristics are very important. A lot of numerical questions can come from this subject. So I try to include maximum variety of questions in this video. So if you found the video useful, please don't forget to like, share and subscribe. And also you can find the notes of this video in the description. So let's see the questions. So this is a mock test of EDC subject. We are going to see the solutions of the 10 questions which you have already seen. The questions you will be seeing on board. The first question is, in a NPN silicon transistor, alpha equal to 0.995, I equal to 10 milliampere and the leakage current ICBO equal to 0.5 microampere. Determine ICEO. So we need to find ICEO, which is a collector to emitter leakage current. We'll write all the given values on board. Alpha is given 0.995. IE, emitter current is given 10 milliamperes. Then ICBO is given 0.5 microampere. And we need to find ICEO. This is a question. So first we will find what is IC. Because we have ICBO and we have alpha, so we can first find IC. So the collector current IC equal to alpha IE plus ICBO. So we have done a detailed video on the equations of BJT and also the numericals that is given in the analog electronics playlist. You can use that video for the reference of these type of questions. So the collector current IC equal to alpha IE, which is the emitter current, plus collector to base leakage current. Okay, so we are going to substitute, all the values are given here. So we'll substitute and find directly what is IC. 0.995 into 10 milliamperes, 10 milliampere plus 0.5 microamperes. Okay, and if you solve it, you will be getting 9.9 9505 milliamperes is the value of IC coming. Okay, we don't need IC, we need ICEO. Okay, so we have the value for IC now. Please note it here. Okay, we'll write it here. IC equal to 9.950 milliamperes. Okay. Next, we'll find what is IB. I'll remove this. Now I'm going to find what is IB, which is the base current. Okay. We know the relation IE equal to total emitter current is the sum of base current plus collector current. So from this we can find what is IB. We have IE and we have IC. So IB equal to IE minus IC, that is 10, both are in milliamperes. So 10 minus 9.9505, that is equal to 0.0495 milliamperes will be the value of base current. Base current will be normally very small value. Okay. So here also the value is very small, 0.0495 milliamperes. Next, we are going to find what is beta. So we have alpha, we can find beta. Okay. So I'm going to note the value of IB here. IB equal to 0.0495 milliamperes. Okay. Next I'm going to find the value of beta. These are current gains, alpha, beta, and the relations also I have discussed in the formula revision video. Okay. So beta is equal to alpha by 1 minus alpha. Substituting the value of alpha in this equation, you will be getting beta as 199. Okay. The value of beta, we have obtained beta equal to 199. So now we have IC, we have IB, we have beta. Now, in order to find ICEO, the equation is actually like this. Total current on collector, or the collector current IC, is equal to beta times IB plus ICEO. We have used this relation in a couple of numericals, which we have already done in various videos. So this is a very famous equation. Total collector current is actually the sum of beta times base current plus the leakage current. Now we need to find this here. So we'll take this term to this side. So the equation will be now IC minus beta IB equal to ICEO. This we actually want to find. So we'll write in the actual form ICEO equal to IC minus, I hope you can see this, or else I'll write it here, ICEO equal to IC minus beta IB. Now we have IC, we have IB, we have beta also. So see, we have written all the values here. Just substitute and find. So IC, I'm going to substitute 9.9505 minus 199 into 0.0495. So what we need for actually doing this equation or solving this equation, we need all these variables. We need IC, we need beta, we need IB. So that's why we have found what is IB, what is IC, and what is beta. And solving this, you'll be getting the value as 100 microamperes approximately. And the correct answer for the first question is option B. This is actually a little bit lengthy question. We can expect this question in higher end examinations. Okay, so by practicing this, you will first get to know these relations, and then you will be familiar with the type of these questions. Okay, so first try to prepare a formula revision note of the BJT. All these equations are important, connecting the currents and also the leakage currents also. So try to form a small formula revision note of the BJT current equations and the gain equations and all, and then try to do these type of numericals. Okay, moving on to the next question. So in EDC you can find a lot of these type of numericals. So moving on to the second question. Second question is comparatively simple question. During reverse bias, a small current develops known as A, forward current, B, reverse current, C, reverse saturation current, D, active current. So the current during reverse bias is called reverse saturation current. Okay. So that is the answer for the question. Correct answer is option C, and the value will be actually in picoamperes. Very minute amount of current will be that. Correct answer is option C, reverse saturation current. Moving on to the third question. Third question is also again from BJT itself. In CB configuration, that is a common base configuration, the value of alpha equal to 0.98, a voltage drop of 4.9 volt is obtained across a resistor of 5K when connected in collector circuit. Find the base current. Okay, so we need to find what is IB. So here again we can use all these relations between IC and IB, and also we don't need, in this question we don't need leakage current. So we don't need that equation. We need the simple equations. Okay. So first we'll try to write all the values given in the question. It is given that the voltage drop of 4.9 obtained across a resistance connected to the collector. Okay. So we can call it as RC. Sorry. Yeah, the resistance is RC and the voltage we can call it as VC. So RC value is 5K and VC value is 4.9 volt. Okay. Now we need to find what is collector current, and if you have the voltage and resistance, directly you can substitute and find the value of collector current, which is 4.9 by 5K it is. So we'll get 0.98 milliamperes. Okay, milli, why? Because there is a K in the denominator. Now, so we have obtained the value of collector current. Now now we have IC is equal to 0.98 milliamperes. Okay, so next also alpha value is given in the question. So we'll try to find out what is IE or the emitter current. The relation is alpha is equal to IC collector current by emitter current. This is the common base current gain. The input current is IE, the output current is IC. So the current gain is alpha, which is output by input current, IC by IE. So from this relation, we'll try to find out what is IE by taking IC by alpha. IC is 0.98 milliamperes by alpha is equal to 0.98. So the answer coming is 1 milliampere is the value for your total emitter current. Okay. So we have now IC and we have now IE equal to 1 milliamperes. So from this we can find the value for IB, right, by using a simple relation IE equal to IC plus IB. So from this you can find what is IB. So I'm going to substitute the values. 1 milliamperes minus 0.98 milliampere again equal to 0.02 milliampere is the value for IB. I hope it is clear. So how to solve this question? So here the voltage and the resistance value of the collector resistance is given. There is a resistance on the collector terminal. Its voltage, the voltage across that resistance and the resistor value itself is given. So from that you can find what is the current through the collector. So we'll get what is collector current. Now we have the collector current and we have the alpha value. So from this relation we'll try to find out what is IE, right? Again, we have this famous relation of the three currents. In that, if you substitute IE and IC, you will get the value of base current. That is a question. So, the answer coming is option C, 0.02 milliamperes. Now, the question answer for the third question is option C. Moving on to the fourth question. The fourth question is, what will be the output of the following circuit? Assume 0.7 voltage drop across the diode. Okay, very simple question. This is the 12 volt. This is a diode. Okay. Now, what is the output coming? By using simple logic, there is a diode, which is a silicon diode, since the voltage drop is 0.7 volt. So, whatever voltage you apply here, right, has to, so this will be, consider that you are connecting a load here. Okay. So, the voltage will be in series in this circuit, right? And the total voltage, which is 12 volt from the source, some voltage will get dropped across the diode and the remaining will come across your open terminal. Here it is open terminal only. So, the voltage coming in this terminal will be actually the difference between this 12 and the whatever drop is coming across the diode. Right. So 12 minus 0.7, which will be 11.3 volt, will be the output. 11.3 volt. Okay. So just you have to use your logic. Total voltage is 12, out of which some voltage will get dropped across the diode. This is again a series combination. So the remaining has to come here only, which will be 11.3 volt, and the correct answer will be option C. Okay. So the fourth question answer is option C. Moving on to the fifth question. Fifth question is from tunnel diodes. The range of tunnel diode voltage VD for which the slope of VI carrier is negative. Okay, so we have discussed in detail in the tunnel diode revision video about the negative resistance region of the VI carrier and about the peak voltage, valley voltage, all these things. So here, what is the voltage VD? It is also given the question, the VP is the peak voltage and VV is the valley voltage. So I'll read out the options. A, VD greater than 0. B, 0D less than VP. C, VV greater than VD greater than VP. D, VD greater than VV. Okay, so if you have no clue or no idea about what is tunnel diode or what is a VI carrier, please do watch that video. That is an analog electronics playlist. I'm sharing the old playlist in the descriptions. If you want to refer any particular videos, please do watch that video in the corresponding playlist. Okay, here the tunnel diode video you can find in the analog electronics playlist. In that video, we have discussed about all these things. So once you watch it, you will be very familiar with this question. So there is a VI carrier. I'll draw the rough diagram. So this is a rough carrier of a tunnel diode. Okay. So there is a voltage here, peak voltage, and this is the valley voltage. Okay. So this is the V. This is the I. Okay. So initially the current will increase and then decrease and then increase. So due to the particular nature of the tunnel diode, and this region we call it as a negative resistance region. Okay. So this voltage is VV, valley voltage, and this is VP. So this region in between these two voltages is called the negative resistance region. So how to define that region is actually the question. So you can write it as, in terms of voltage, VV is greater than VD. If you call this voltage as VD, the range is between this. Okay, so this is the correct answer. Okay, I hope you understood the question. The question is to define the range of this negative resistance region's voltage. So it will fall in between VV and VP, right? So the higher voltage is this. This is the voltage axis. So higher voltage is VV, lower voltage is VP. So in between that, the VD is lying. Correct answer is option C. Moving on to the sixth question. Okay. Which of the following can be used in series with a Zener diode so that the combination has almost zero temperature coefficient? So this question is a theory question. So what combination can be used with a Zener diode so that its temperature coefficient is negative? Options: A diode, B resistor, C transistor, D MOSFET. So in order to nullify the temperature coefficient or the temperature coefficient changes, we use a diode in series with a Zener diode. Correct answer is option A, because diodes have positive temperature coefficient whereas Zener is having negative. So if both this combines, they get nullifies. So correct answer is option A, diode. So that is the answer for your sixth question, which is option A is the answer for your sixth question. Now moving on to the seventh question. Seventh question is a numerical type of question. Calculate the recombination rate if the excess carrier concentration is 10 raised to 4 centimeter raised to minus 3 and the carrier lifetime is 1 microseconds. So what all things are given? the concentration is given. We'll call it as Dn. Concentration is 10 raised to 14 centimeter raised to minus 3. And the lifetime of the carrier is given. We'll call it by the letter tau, 10 raised to minus 6 seconds. Micro means 10 raised to minus 6. So 10 raised to minus 6 seconds is the lifetime. We need to find the recombination rate. The equation is, please note it if you don't know, the recombination rate of the carriers or the excess carriers is R equal to the concentration by lifetime. That is dou n by tau. So it will be 10 raised to 14 by 10 raised to minus 6. That is 10 raised to 20. Okay. So correct answer is option C. 10 raised to 20 is the recombination rate. So 7th question, correct answer is option C, 10 raised to 20. Now, moving on to the 8th question. Calculate the diffusion current density. That is, we need to find the current density in this question. It is again a numerical question. Calculate the diffusion current density when the concentration of the electron varies from 1 into 10 raised to 80 to 7 into 10 raised to 17 centimeter raised to minus 3 over a distance of 0.10 centimeter, and the diffusion constant D is given 225 centimeter square per second. So we'll first write what is the equation for the diffusion current density. J equal to E, which is a charge of an electron, into diffusion constant into variation in the number of charge carriers or the electrons, or n type, electrons by dx. That's the variation. Okay, with distance. So we will substitute all these values because all the values are given in the question. Okay, so what is E? E is a charge of an electron. That is not given in the question, but you should be knowing it. 1.6 into 10 raised to minus 19, right? Into D is given in the question, which is 225. Then into, now this is the change in the concentration. Okay, so it is given in the question that the concentration of electron varies from 1 into 10 raised to 18 to 7 into 10 raised to 17. So it is 10 raised to 18 minus 7 into 10 raised to 17 by 0.1. Okay. So this is the 0.1. So all the values are given in centimeters. So you don't need to change. Okay. So I have substituted all the values here. And if you solve it, the value getting is 108 ampere per centimeter square. Current density is current by area. So current unit is ampere. Then area is centimeter square. So it is ampere per centimeter square. So it is 108 ampere per centimeter square is the diffusion current density. Correct answer is option B. 8th question, correct answer is option B. Now moving on to the 9th question. So I have tried to include a lot of numericals in this video because a lot of people was asking for numerical type of question. Moving on to the 9th question. Transformer utilization factor of a half wave rectifier. This is a theory question. The question is asking the transformer utilization factor or TUF of a half wave rectifier. This value you should be knowing. 0.287 is the transformer utilization factor for a half wave rectifier. Correct answer is option C. Okay. So 9th question, correct answer is option C. Moving on to the 10th question.